Good afternoon, friends. We are discussing last time Fourier series. Fourier series represents basically is a representation of a periodic function in terms of cosine and sine functions of different frequencies. The frequencies are multiples of one fundamental frequency. So, we wrote yt as a0 plus summation an cosine n omega naught t plus bn sine n omega naught t, where n varies from 1 to infinity. Now, this representation gives me the coefficients an and bn including a0 as 1 by t integration over t this function yt multiplied by the corresponding orthogonal function. Say if I want to evaluate an, it is to be multiplied by cos n omega naught t. If it is bn, then to be multiplied by sin n omega naught t and then integrated over this period. And if it is a naught, then a naught is multiplied by just a constant. So, you have to just integrate this, and that gives me the coefficients a0, an and bn. We have used the properties of orthogonal functions. Now, one may express cosine n omega naught t and sin n omega naught t in terms of exponential functions. Similarly, sin n omega naught t as e to the power j n omega naught t minus e to the power minus j n omega naught t by 2j. If we express the functions sine and cosine functions in terms of the exponential functions and substitute here, what we get is yt as a0 plus an for cosine n omega naught t. I will substitute this e to the power j n omega naught t plus e to the power minus j n omega naught t by 2 plus bn into e to the power j n omega naught t minus e to the power minus j n omega naught t divided by 2j. If you allow me to segregate the exponential terms, a0 I can write this is 1 to infinity an bn by 2j and an by 2. So, I will write minus j bn by 2 e to the power j n omega naught t plus an e to the power minus j n omega naught t by 2 bn minus this quantity divided by 2j. So, if j is brought up, it will be plus j bn by 2 e to the power minus j n omega naught t. Okay. So, we can express in terms of two exponential terms and the coefficients will be just complex conjugates. One may write this as C0 plus Cn. I will write Cn bar as an minus jbn by 2 if this is C n bar, then this is C n bar minus, I will put minus one to infinity. Is it all right? So, one may write this as C n e to the power j n omega naught t, n varying from minus infinity to plus infinity, where both of them are taken together, where C minus n means a n minus j b n by a n plus j b n by 2, that is complex conjugate of this. Where C n bar is 1 by t 0 to t f t e to the power minus j n omega naught t dt. Do you agree? Let us see how we get this. C n bar is C n is a n minus j b n by 2. So, if we write in terms of those coefficients, it is f t cosine n omega naught t dt minus j by j into b n by 2. So, j by t 0 to t f t sin n omega naught t dt. Is it all right? So, that gives me 1 by t 0 to t f t cosine n omega naught t minus j sin n omega naught t dt. So, this is nothing but e to the power minus j n omega naught t. So, this is what we have written, f t into e to the power minus j n omega naught t dt. C n bar magnitude will be half of, you can see, a n squared plus b n squared under root by 2 that is old C n by 2. If you remember, when we expressed these quantities together by C n earlier, we had written plus phi n in this form, where C n square is a n square plus b n square under root. Here it is that divided by 2. So, old C n by 2 is C n bar magnitude, and phi n here, if you can write C n as C n bar magnitude and e to the power j phi n, then phi n is tan inverse b n by a n with a negative sign. C minus n is C n magnitude e to the power minus j phi n is nothing but C n star. Now, in a Fourier series representation, you are taking an infinite sequence. Physically, it is not possible to consider an infinite sequence always. So, we somehow we have to truncate somewhere. So, what is the error involved when you go for a truncation? Now, any series f t, if you express any periodic series, I mean any periodic function, if you express in terms of Fourier series a n cos n omega naught t plus b n sin n omega naught t. Suppose we truncate it after 20 terms, that means we consider only the first 20 terms and then after that we drop them. The magnitudes of these coefficients a n and b n may be very, very small, so you can drop them. Then how much is the error incurred? So, error, if we consider from nth harmonic onward, then what is the error? Error will be, will take the original function minus the aggregate of the terms up to that nth term, up to the 20th term, say. So, that much error, if you take the square of this error, all right, that will give me some measure of, we can take the mean square error, say, as a measure of performance, representation. So, E n will be f t minus sum of, say, nth order harmonics up to nth order, sum of terms up to nth order harmonic. Okay. Therefore, mean square error if you call it capital E n, that is up to nth order, we are considering is 1 by t 0 to t, this error E n squared dt. Now, is there any other representation which can give me up to 20th term a better representation of the signal? That means, if we consider up to 20th term some other series, some other functions, some other combinations, can we get a better series, better approximation, so that the error will be minimum? It can be shown that if we minimize this error, minimization of this error gives me that the series that we have considered in this sum, this truncated series, the coefficients of the truncated series is the coefficient of the Fourier series, original Fourier series. That means, if you consider Fourier series, if you truncate it, the truncated series is the best possible series that can express the function, given function, in a least square sense, in a least square sense of the error. So, minimum E n gives me the Fourier coefficients as the best possible choice. Now, next we take up another issue. How do the coefficients change in magnitude as we go down in the derivative functions? That means, if f t is a function given by a series like this, f dash t its derivative, f double dash t, and so on. If we consider, these are also periodic functions, if we consider these functions, how will the coefficients a n's and b n's in these respective series, how will these coefficients vary with n? Let us take f t. Once again, a n cosine n omega naught t. Let us consider only the first term. Then what will be f dash t? It will be n omega naught a n cosine n omega naught t. Similarly for b n terms. Now, if the earlier coefficient had been a n, now it is a n into n omega naught. That means as n increases, the coefficient, the importance of the coefficient is enhanced, it is increased. For example, if for ft the coefficients are, say let us consider only a coefficients, I will consider ai magnitudes. So, a0, a1, a2 and so on, a3. Suppose these are the coefficients and this is for ft. Then for f dash t, the same coefficients, a0 may not be present, in this case it will not be present, a1 you say this much, a1 gets multiplied by n is 1, then a2 will get multiplied by 2 times omega naught, a3 will be multiplied by 3 times omega naught and so on. So, depending on the value of omega naught and also they are multiplied by the harmonic number. So, these gain importance. Higher harmonics do have an enhanced importance in f dash t. If you go further down, then it will be increasing further. That means it will contain, it will be rich in harmonics. As you go to further and further derivatives, you will have harmonic rich signals. Let us see what that means. Let us take a square function. Square wave like this. Now, it may have, say, coefficients may be bn, in this case it will be, it is an odd function. So, it will be consisting of only sine terms. Suppose these are the coefficients, and so on. Then what is derivative of ft? Derivative of ft will be a delta function here, delta function here, a delta function there and so on. Actually it is coming from this point to this point. So, they will be of same magnitude. Okay. That means you are finally coming to only impulses, and impulse, as you know, there is a very sharp change that is taking place. A sharp change means there will be large number of harmonics. On the other hand, if you integrate this, if you would have gone just one step higher, f t integral, then what would have been the function like? It is a triangular function and so on. So, what will be the harmonic component for this? Whatever harmonic components we had for this f t, now it will be, say, cosine or sine n omega naught t bn. This is to be integrated. If I integrate this, I get this. So, in the series if I integrate this, it will be Bn by n omega naught, okay, sin n omega naught t. So, as n increases, the magnitude of this coefficient will be decreasing. So, coefficients for this will be decreasing very fast. Okay. If you integrate it further, it will be, say, as we integrate this, it is a parabolic function. You can see it is very smooth, very much like a sine wave. So, a smooth function means it contains less of harmonics. So, the fundamental will be very high. It may have a DC value also, because now it is integrating, and it integrating this, you get positive area, and then that starts reducing, it becomes 0 here, it never becomes negative. So, it is always having some average value. So, it will have this, and then this is further increased compared to this, their relative magnitudes will be much smaller. So, as you keep on integrating, you have less number of harmonics. As you differentiate, you have more number of harmonics. That means the harmonics that we are earlier neglecting cannot be neglected as you go to derivative functions. This is very important. Now, we will consider some applications of Fourier series in network functions, in network problems. We excite a network by a square wave like this. Say network may consist of R and C, or a simple network we can consider, say, R and L. There are two networks, say Z1 and Z2. What will be the response if this is the voltage applied, periodic voltage applied across these two networks? What will be the current like? Now, one way of solving this is calculate Vs, that is the Laplace transform of this, calculate the impedance in the S domain, that is Z1s or Z2s, then Vs by Zs will give me corresponding Is, take Laplace inverse of Is, that will give you It. Now, we are interested in the steady state value. That means, at steady state, when the transients have died down, what would be the magnitude of this current It? What will be the expression for It? Now, instead of going by this Laplace transform and then taking inverse, we may find out the Fourier series, the Fourier components for this periodic function. So, Vt we can express in terms of A0 plus say A1 cos omega naught t and so on, and in this particular case Bn terms will be 0, otherwise Bn terms will also be present. Then for each frequency we calculate what will be the corresponding Z j omega. Okay. For different frequencies at j omega naught, 2 j omega naught, 3 j omega naught, etc. We calculate the complex impedance. Once you know the complex impedance, the voltage component divided by the corresponding impedance gives you the component of current at that frequency. So, now we can apply superposition theorem, take all the currents together and then we can add them together. Okay. So, let us take this very example. Vt we can write as cosine t minus 1/3 cosine 3t plus 1 by 5 sin 5t and so on. Let us take the first voltage of magnitude V1, which will be, we may take RMS value or we may take maximum value, because finally we shall be writing the expression for current. V3 will be 1 by 3 and angle, this is minus, so minus 180 degrees. V5 will be 1 by 5, angle, this is plus, so 0 and so on. So, what will be the current I1 in the RMS sense, in the maximum value sense? We are not taking the RMS value. If you take the RMS value, divide it by root 2. So, I1 will be V1 by Z1, if I call it Z1. Similarly, I3 will be V3 by Z3, where Z1, Z3, Z5 mean, by this we mean the value of the impedance, complex impedance at the first harmonic, fundamental, third harmonic, fifth harmonic and so on, and the corresponding frequencies are known. Omega 0 is 1, omega this is 3 times omega, omega naught, 5 times omega naught and so on. So, in this case, suppose we have a resistance of 5 ohms and then inductance of 1 Henry. So, Z1, okay, Zs will be 5 plus 1 into S. So, Z1 will be Z at j omega naught, okay. Omega naught is 1, cos 1 into t. So, 5 plus j omega naught, 1 into S. So, 1 is the inductance value. So, it is multiplied by 1, 5 plus j omega naught, and that is nothing but 5 plus j, omega naught is 1. Z3 will be similarly 5 plus 3j, this is 3j. Z5 will be 5 plus 5j and so on. So, correspondingly currents will be V1 by Z1, which is 1 angle 0 by 5 plus j. If you permit me, this is 1 plus 5 plus j, so root over of 26. So, approximately 1 by 5, so 0.2 and an angle of tan inverse 5, 1 by 5. So, about 70, about 12 degrees minus. I3 similarly will be V3 by Z3, and V3 is 1/3 minus 180 and Z3 will be 5 plus 3j. So 25 plus 9 under root, so under root 34, so that is approximately 5.8. Okay. So 1 by 3 into 5.8 and an angle of tan inverse 3 by 5. So tan inverse 0.6. So pretty close to 30 degrees. Somewhere 35 degrees or so. Okay, let us say 35 degrees. So I have just taken a rough value. You can evaluate these 1 by 3, 5.8, and this 35 will go up. Similarly, I5 will be 1 by 5, angle of 0 degree, and this is 5 plus j5. So 5 root 2 and an angle of 45 degrees. Okay. Therefore, IT can be written as superposition of these components will give me 0.2 cosine t minus 12 degrees plus 1 by 3.33 by 5.8, so approximately 6, so 0.05. Very crude approximation, a little more than 0.05, okay, and angle of minus 45 degrees, sorry, 0.05 cosine 3 t minus 45 degrees. Similarly, plus 1 by 5 root 2, 1 by 25 root 2, whatever be that value, sorry, 45 degrees will come here, here it is 35 degrees. Mind you, this will be 180 degree will contribute to a negative term. So, I may put this as minus whatever be this value 1 by 3 into 5.8 and an angle of minus 35 degrees. Okay. So, it will be minus this value cosine 3t minus 35 degrees plus, again it comes back to 0 angle. So, plus this quantity 1 by 5 25 root 2 cosine 5t minus 45 degrees and so on. So, this will be the total sum of the currents. So, this is a very handy method for computing the component the current in the time domain for periodic functions, when you excite it by periodic functions under steady state conditions. Now, we define power spectrum. When we see frequency spectrum, that is when you arrange the Fourier coefficients in terms of against frequencies, we get a line spectrum. Now, if we take the power, effective power for each component, then that gives me what what is known as power spectrum. So, f t is say C 0 plus 2 into C n cosine n omega naught t plus phi n. You can write like this, sine and cosine terms put together will appear like this. And C n was basically half of A n plus j b n or A n minus j b n. So, f effective, when you talk about effective value, it is basically the heating value. When we pass a current through a resistance, then how much is the effective value of the current? We measure the effectiveness in terms of the amount of heat dissipated. So, square of that function over this interval t and then take the average, that is f effective. So, that is equal to 1 by t over t C 0 plus twice C n squared, okay, C n cos n omega naught t plus phi n whole thing squared into dt. When you take an integral of this kind, so a plus something like a plus b cosine omega t squared dt over a period t, one term you get is a square, the other one is b square cos square omega t, the third one is twice a b cos omega t, integrate. This will give me a square constant, this is b square cos square omega t. I can write this as in terms of cos 2 omega naught t, okay, plus 1 by 2. So, I can substitute that and then twice a b cos omega t dt. So, cosine omega t dt integrated over one period is 0. Similarly, cosine 2 omega t will also give me 0 because they are orthogonal functions. So, average value over one time period is 0. So, we are making use of that property, and finally, it boils down to, in this case, this constant squared plus 2 into this constant square. So, it will be C 0 squared plus 2 into sigma C n square. This is the maximum value of the cosine function C n. You can also express in terms of RMS value. I RMS is equal to I max by root 2. So, I effective squared will be I effective 1 squared plus I effective 2 squared plus I effective 3 square and so. That is, if you are having a harmonic rich signal, you want to find out the power spectrum, you take each harmonic and corresponding effective values, square them up, and addition of that will be the overall effective value squared. So, I effective will be square root of I effective 1 square plus I effective 2 square and so on. In a network, the power will be, suppose you have got the expression for V t as V 0 plus V 1 cosine omega naught t plus phi 1 plus V 2 cosine 2 omega naught t plus phi 2 and so on, and I t as I naught plus I 1 cosine omega naught t plus theta 1 plus I 2 cosine 2 omega naught t plus theta 2 and so on. Then average power is 1 by t integrated over t V t I t dt, and this will be, you can see if you integrate this with this, V 0 with I 2, V 2 with I 1, these terms will be giving me an effective value 0, because there are different frequencies. We are taking the product of cosine functions of two different frequencies, then taking average over one period. So, it will be 0 by orthogonal property. So, cosine omega naught t will be coming with this cosine omega naught t terms, cosine 2 omega naught t will come with cosine 2 omega naught t terms and so on. So, finally, the effective power will be V 0 with I 0, whatever is the effective power, V 1 I 1, obviously the power is V 1 I 1 cosine of the angle between the two, phi 1 minus theta 1, phi 2 minus theta 2 and so on. So, that will be the effective value of power. So, P average is equal to P average 1 plus P average 2 and so on, the average of all these powers, individual components, that will be the average power. Now, this is all about Fourier series. We have talked about periodic functions. Now, can we stretch it a little beyond this? We have considered a periodic function, say like this. The period was t, and in the frequency spectrum we got lines. This gap is omega naught between two successive frequencies that are present here. The gap is omega naught. Suppose we consider power frequency 50 hertz, then it will be 0, 50 hertz, 100 hertz, 150 hertz and so on. These are the frequencies present, and that frequency corresponds to this t. 1 by t is that fundamental frequency. Now, suppose we have this t magnitude is reduced, this period is reduced, that means corresponding frequency has been increased. That means this gap has been increased. So, the spectrum will be like this. Okay. On the other hand, if we stretch it, if we stretch t, then this will be shrinking, the gap will be narrowed down. So, these lines will be coming closer. So, let us consider a function which is not periodic, we call them aperiodic function. Suppose we have a function like this. One may assume this to be a part of a periodic function whose period is very, very large. That means, as if this function is going to repeat like this, but this period is very, very long. It is a part of a very long period wave. That means, this function I have assumed it repeats after a long time, maybe after 1 year, 2 years. So, this is 1 year or 2 years. That means, it remains 0 for a large time. It is as good as considering this aperiodic function as it is. So, if we assume this to be a part of a periodic function of very large period, then what happens to the frequency spectrum? Frequency spectrum, these lines are coming very, very close, is it not? These lines will become closer and closer because omega naught is reduced very much, and in the limit we shall be getting a continuous frequency spectrum. These values, if these components, if they come very, very close to each other, then it will generate a continuous function like this. A continuous function like this for an aperiodic function f t, for an aperiodic function in the frequency domain, the representation is no more n, because they are very, very close. So, we cannot count them. So, they are as good as a continuous function. So, f omega against omega will be a continuous function. So, an aperiodic function instead of Fourier series, we call this as Fourier transform. A Fourier transform is basically frequency domain representation of an aperiodic function. In this, all possible frequencies are present. That means, an aperiodic function can be thought of an aggregate of a large number of frequencies, infinite number of frequencies of different magnitudes. There is a phase also associated with each magnitude. So, an infinite number of sinusoids will compose this function. All right. So, this is known as Fourier transform. We shall not go into the details of Fourier transform in this class. We shall restrict ourselves to Fourier series. Now, some of the interesting series that we come across in practical systems will be some of the periodic functions other than sinusoids is a rectified sine wave, half wave, rectified sine wave, then full wave, rectified sine wave, then also gate fired pulses, these sinusoidal functions are fired by gate. So, they are all chopped. There are signals of this kind generated from power electronic drives. This is periodic, this is also periodic, this is also periodic. Sorry. All these are examples of periodic waves that we come across in electrical engineering in practical situations, and they give rise to harmonics. If we decompose them into Fourier analysis, into Fourier series, we get large number of harmonics or sawtooth wave. Sometimes we generate this type of periodic functions also in the laboratories for various studies. So, all these will give rise to harmonics, and harmonics disturb the system. If the system gets too many harmonics, then there are many equipments which are to be protected against harmonics. So, you have to design filters to suppress those harmonics. So, low pass filters are provided in a large number of equipments to suppress these harmonics. So, we should have a low pass filter which will allow only 50 hertz, and nothing beyond, alright. So, the harmonics that will be generated here are 50, 100, 150 and so on. So, they are all to be suppressed for the protection of equipments. This is a very important area of application of Fourier series in networks, electrical networks. It is also in mechanical systems. Sometimes say we have a reciprocating motion, a diesel engine or any IC engine, or many drives where you have a reciprocating motion. So, that causes some kind of a vibration, alright. It is a periodic function, but it is not a sinusoidal function. So, any periodic function we can decompose into large number of harmonics. So, a mechanical system, say a shaft is rotating at 500 rpm. Because of some eccentricity, it is having a vibration, alright, or it is maybe having a ram which is moving corresponding to that speed, alright, which is giving you a non-sinusoidal motion. So, you can decompose that into harmonics. So, multiples of 500 rpm, that is 1000, 1500, those frequencies are also present and they will give rise to some kind of a vibration. Sometimes to protect the equipments we need to suppress those vibrations, high frequency vibrations. So, we need mechanical filters, shock absorbers. These are the mechanical analog of electrical filters. We use dampers, then mass, spring and dashpot. These are the three equivalent items. Mass corresponds to inductance, a dashpot corresponds to a resistance, and a spring corresponds to a capacitance in electrical network. So, with the help of these three elements, you can always design a filter to suppress some of the harmonics and to protect the equipments from vibration, because there may be some frequencies at which the system frequency, the system's natural frequency may be very close to some of these harmonics, then the system will start resonating. So, to stop resonance of mechanical systems, you have to suppress those higher harmonics. So, that is why we protect many of mechanical systems from resonance phenomenon with the help of such shock absorbing such filters, mechanical filters. Shock absorbers are also basically doing the same thing. So, this is all about Fourier series and applications. Thank you very much. We will take up mechanical systems in the next class.
It is no wonder that the Institute is the most preferred campus for technical recruitment of quality manpower. With infrastructure like industrial power and communication facilities, in addition to its excellent research and consultancy facilities, STEP, or Science and Technology Entrepreneurs Park, aims to assist the budding entrepreneur into a successful adventure capitalist, guiding him right from the concept, institutional financing, production, leading up to the launch and marketing of the product. With its rich pool of talent and excellent infrastructure, it is no surprise that through the last 3 decades, IIT Kharagpur has developed strong liaison with the industry. SRIC, or Sponsored Research and Industrial Consultancy Cell, was formalized as the Special Industry Interaction Cell in 1982. Devoted full-time to handle industrial projects and consultancies and for deploying and propagating intellectual property. Successful sponsored research projects straddle a wide spectrum, ranging from computers, communication and biotechnology to robotics, photonics and food processing. The setting up of a state-of-the-art VLSI CAD laboratory and tie-ups with GE in areas ranging from vehicle structure design to electrical communication and software technologies are excellent examples of IIT Kharagpur's ever-evolving pioneering spirit. Collaborations with a host of national and industrial majors are a testimony of its proven expertise and research repertoire. Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.